Good morning everyone. We are looking into the problems of non-homogeneous partial differential equations and the solutions of those, and in the last few classes we have solved those types of problems using Green's function method. And the typical example we have looked into, there are two types of problems that one can encounter. One is transient problems. Okay, the transient problems means it will be involving one dimension in time, one or more dimensions in space, or steady state problem, steady state multidimensional problems. That means the independent variable temperature or concentration may be function of x and y both, but it will be independent of time. So, in that case also you will be getting the a partial differential equation, and the corresponding operator is a Laplacian operator when it is a steady state problem. Now, more often the steady state problem may not be important, the transient problem is important. Okay. Like the example I was giving, you are having a nuclear fuel element, and which temperature is a function of r and t, and z dimension is so long that all the variations of temperature in the z direction is negligibly small. So, in this case the governing equation will be a function of r and time. Okay, so, it is a function of time and a function of space. Now, so this kind of parabolic non-homogeneous transport equations are important in many cases. Okay. So, and if there is a volumetric heat generation term, you will be getting a generalized non-homogeneous term on the right hand side of your governing equation. The typical form of this equation is, let us say del u, u is the temperature, del u del t minus del square u del x square is equal to f of x and t. Okay. In this case, it is basically you are considering a slab located between x equal to 0, let us say between x equal to 1, okay, non-dimensional length. So, if it is a cylinder, this operator will be replaced by the corresponding cylindrical polar coordinate 1 over r del del r of r del u del r. Now, for simplicity, we have considered it is a Cartesian coordinate, and we are looking into the, and there will be a heat generation term which may be a function of x and t, which may be a function of x, which may be a function of time alone, or may be uniform throughout the whole volume of the system. And we are looking into the solution of u as a function of time and space. Let us say subject to all sorts of non-homogeneities at time t equal to 0, u may be in general function of x, u may be a constant as well. Okay. At x equal to 0, u is equal to p, at x equal to 1, u is equal to q. So, we are having a non-homogeneous governing equation and all the non-homogeneous initial and boundary conditions. Now, we are going to solve this set of equations by using the Green's function method. Okay. So, the first step of this kind of problem is you have to construct the causal Green's function. Okay. What is the causal Green's function? It will be the operator is basically your del del t minus del square del x square. Okay. So, causal Green's function will be del g x t x 0 t 0 del t minus del square g del x square is equal to delta x minus x naught delta t minus t naught. Okay. That will be the governing equation of causal Green's function subject to all homogeneous boundary and initial conditions. At time t equal to 0, your g is equal to 0, at x equal to 0 and at x equal to 1, we are having g equal to 0. Okay. Now, as we have discussed in the last class, that whenever you will be having a partial differential equation whose domains are bounded, then you are going to use full eigenfunction expansion to estimate the Green's function. and whenever you will be having one independent variable bounded and another unbounded, then you are going to use the partial eigenfunction expansion as the method to estimate the Green's function. So, in this case my x domain is bounded between 0 to 1 and time domain is unbounded from 0 onwards. So, one has to use the partial eigenfunction expansion method to estimate Green's function. Okay. You cannot use a full eigenfunction expansion method in this case, because in full eigenfunction expansion you must be considering a a standard eigenvalue problem in both the directions. You cannot have a standard eigenvalue problem in both the direction in this case, because the boundaries are not defined on T. One boundary is defined and that is only required, the other boundary nobody knows, and that is also not recorded by the problem itself. Okay. So, one has to use a partial eigenfunction expansion method to estimate Green's function in this case. So, what is partial eigenfunction expansion method? Remember, we consider in the previous case in full eigenfunction expansion method, we considered the corresponding eigenvalue problem in both the directions. In this case, we will be considering the corresponding eigenvalue problem in the bounded domain only. In bounded domain, that means in x domain. Okay. In x domain, what is the operator? Minus del square del x square. Okay. So, it will be minus d square phi n dx square. Since you are considering the corresponding eigenvalue problem in bounded domain only, x direction. So, the derivative will be a total derivative, it will be with respect to x only, d square phi n dx square minus let us say lambda n square phi n is equal to 0, right. We have solved this type of problems previously. So, this will be the standard eigenvalue problem in the x direction subject to the boundary conditions of your Green's function in the x direction. What are those? At x equal to 0, phi n is equal to 0, at x equal to 1, your phi n is equal to 0. So, what are the eigenvalues? We have solved this problem number of times. The eigenvalues are n pi by 1 and eigenfunctions are, let us say, some constant sin n pi x. Okay. Now, once you get this, then you can express your Green's function as the summation of all these eigenfunctions, with a coefficient attached in front of it, and that coefficient in this case will be a function of time. In the previous case, it was a two variable problem and you had complete eigenfunction expansion. So, that coefficient was independent of any independent variable, but in this case, since you are having eigenfunction expansion in only one direction and expressing your Green's function as a summation of all these eigenfunctions, then your corresponding coefficient must be function of time, the other variable which you have not considered. So, your Green's function can be expressed as g x t slash x 0 t 0 is nothing but summation of all these eigenfunctions phi n x, where n runs from 1 to infinity, and this coefficient will be function of time. That will be the formulation of Green's function using partial eigenfunction expansion. Okay. And phi n is basically sin n pi x, and sin n pi x, sin functions are always orthogonal to each other. Okay. So, a n can be estimated as an integral of g and phi n over dx divided by phi n square over dx, right. So, you can, since they are orthogonal, you can open up this summation series, and apart from one term all the terms will vanish. Okay. Now, this integration is over x from 0 to 1, and you can force your eigenfunctions to be orthonormal, so that this denominator will become 1. So, in this case it will be 0 to 1 phi n square is basically c n square sin square n pi x dx is equal to 1. Okay. Force the eigenfunctions to be orthonormal. So, it will be nothing but sin c n square by 2 is equal to 1. So, c n is equal to root over 2, right. So, what are the eigenfunctions? The eigenfunctions will be nothing but root over 2 sin n pi x. These eigenfunctions are orthogonal as well as orthonormal. Okay. So, what simplification it will lead to? It will lead to the denominator of a n, which will be a function of time, the denominator will become 1. Okay. Phi n dx. Okay. Now, you have to find out what is this integral, the g phi n dx. For that, what you have to do? You have to multiply the governing equation of Green's function, that del g del t minus del square g del x square equal to del x minus x naught into del t minus t naught. You multiply both sides of that equation by phi n dx and integrate. Okay. And integrate which over what? Integrate over domain of x from 0 to 1. So, it will be phi n del g del t dx minus del square g del x square phi n dx is equal to phi n x naught delta t minus t naught, right. That is a shifting property of the Dirac delta function. So, this from 0 to 1, this from 0 to 1. Now, what is this? This integration is over x. So, it does not hamper the derivative with respect to time. So, this becomes d dt, this del del t becomes d dt from 0 to 1 phi n g dx, because after integration over x, and it is a definite integral from 0 to 1, it will be independent of x once you evaluate, put the limits. So, it will be function of time alone. So, partial derivative becomes a total derivative with respect to time. If you remember, you have done this type of mathematics in solution of boundary layer analysis by integral method. Professor Dasgupta must have done that, or it will be done in the transport phenomena too. Have you done that? No. Okay. So, it will be covered in TP2, but this is quite simple, right. So, del del t will be becomes d dt, and it will be out of the integral sign, because the integration over x. Okay. Minus first function, integration of the second function by parts, del g del x, first function, integration of second function, phi n is the first function from 0 to 1, minus differential of first function, that is d phi n dx, integration of second function, that is del g del x dx from 0 to 1 is equal to phi n x naught delta t minus t naught. Okay. Is it right? So, you can, so what is phi n? Phi n at x equal to 1 is 0, phi n at x equal to 0 is 0. So, there is no contribution from this term. Okay. Say minus minus plus, one more integration by parts of this term, that will lead to what? Let us see, d dt of integration 0 to 1 phi n g dx minus minus plus del phi n del x del g del x dx from 0 to 1 phi n x naught delta t minus t naught. Okay. So, this will be d dt 0 to 1 phi n g dx plus first function integration of the second function. Okay. This will be d phi n dx, okay, because phi n is a function of x alone. So, there is no partial derivative. So, first function integration of the second function, del g del x is the second function, let us consider. So, that will be g only from 0 to 1 minus 0 to 1 differentiation of the first function, that is d square phi n dx square. Okay. So, d square phi n dx square times g integration of the second function times dx, right, is phi n x naught delta t minus t naught, right. Now, g at x equal to 1 is equal to 0, g at x equal to 0 because whenever you are constructing the Green's function, its boundary conditions have to be homogeneous. So, again there is no contribution from this term. Now, look into the governing equation of phi n, that is d square phi n dx square is equal to plus lambda n square phi n equal to 0. Okay. So, d square phi n dx square is equal to nothing but minus lambda n square phi n. So, minus minus plus. So, this becomes d dt of 0 to 1 phi n g dx minus minus plus lambda n square 0 to 1 phi n g dx is equal to phi n x naught delta t minus t naught. Okay. Now, what is phi n g? Right, n, which is basically a function of time, right. So, I will be replacing integration g phi n dx by a n, which is a sole function of time. So, this becomes d a n dt plus lambda n square a n is equal to phi n at x naught delta t minus t naught, right. So, this is the governing equation to estimate a n. If a n is estimated, then you can estimate the Green's function as well. That is right. Now, you know how to solve this equation. T naught is a point where you have a discontinuity. So, this solution of a n will be broken into two parts. This is a ODE using Green's function, if you remember that example. So, it will be constituted by two parts. One part will be less than 0 to t naught, another will be greater than t naught. So, d a n dt plus lambda n square a n is equal to 0 for t less than t naught, right. What is the solution of this? That will be the solution. Okay. For t greater than t naught, right, the same equation will be holding good. This right hand side will be equal to 0 because you are putting a unit impulse at t equal to 0, t equal to t0. So, you will be getting a n, but with a defined constant, let us say b exponential minus lambda n square t for t greater than t naught. Now, you have one condition, if you remember, that Green's function is 0 at time t equal to 0, right. That means, at time t equal to 0, your g was 0. That means, a n, this constant a, this a constant a n must vanish at time t equal to 0, otherwise Green's function cannot be equal to 0, right. So, this will lead to the constant a to be equal to 0, okay. And the constant, so basically for time t greater than t naught, you are having a solution a n is equal to b exponential minus lambda n square t. Now, b is basically non-zero and it will be contributing something. Now, you do not know another condition on t, because you know only one condition on t at time t equal to 0. For that, you have to what you have to do, you have to use the jump discontinuity condition. Okay. This is a condition which relates the derivative of the time varying part before t naught minus and t naught plus. Okay. So, it will be d a n dt dt, you integrate the governing equation of a n between t 0 minus and t 0 plus, okay, t 0 minus epsilon and t 0 plus epsilon. Right. What will be this? This will be a n at t 0 plus minus a n at t 0 minus. In the limit, this term will be gone. Okay. So, plus lambda n square times 0, and what will be this? This will be integration over t, phi n x naught is considered to be constant. So, this will be becomes phi n x naught only, and it is a Dirac delta function, integration over it about the that impulse point. So, it will become 1. And what is a n t 0 minus? It will be 0, that is correct. So, a n t 0 plus is nothing but root over 2 sin n pi x naught. Okay. So, now you use the continuity of Green's function at time t naught plus. And what is your a n? A n is nothing but b exponential minus lambda n square t, right. So, root over 2 b exponential minus lambda n square t naught should be equal to root over 2 sin n pi x naught. Agreed? So, from that you will be getting the expression for b. So, b you will be getting root over 2 sin n pi x naught exponential lambda n square t naught. That will be the, and lambda n is basically n pi. So, it will be n square pi square t naught. Okay. Once you get b, then your Green's function is estimated, because once you get b, then your a n is estimated. So, in turn you will be getting the expression of Green's function. So, Green's function can be written as g x t x naught t naught is equal to 0 for t less than t naught, and this is equal to summation n equal to 1 to infinity root over 2 sin n pi x naught exponential minus lambda n square t minus t naught, okay, times sin n pi x, right, for t greater than t naught. It will be minus only, okay. And you check the algebra whether this will be root 2 or 2, because your eigenfunction in front of it you are having a root 2. So, one root 2 will be associated with sin n pi x naught, another will be associated with sin n pi x. So, this will be probably 2, is it? Just check that algebra. Okay. Now, in a compact form, this is known, this can be written as h t minus t naught summation of root over 2. I am just keeping it root over 2, it may be 2 as well. Okay. So, n equal to 1 to infinity sin n pi x naught sin n pi x e to the power minus n square pi square t minus t naught. Now, this h t minus t naught is known as a Heaviside function. It will be 2, that is correct. So, one root 2 will be coming from sin n pi x naught, another will be coming from sin n pi x, because eigenfunctions are orthonormal and the coefficient coming in front of it is root 2. So, it will be root 2 square. So, it will be 2. Okay. Now, this h is called a Heaviside function. It is defined as h t minus t naught is equal to 0 for t less than t naught and is equal to 1 for t greater than t naught. This is a notation only. So, these two expressions can be written in a compact form by only one expression. It is only a mathematical notation, nothing else. You can keep these two as well if that is clear to you. Okay. Now, you have decided, you have derived the expression of analytical expression of Green's function. Now, what you have to do? You have to find out the adjoint Green's function. If your operator is a self adjoint operator, you need not to evaluate the adjoint Green's function. Now, in the previous example, we had a Laplacian operator which turned out to be a self adjoint operator. Now, in this case, the parabolic operator, let us check whether it is a self adjoint operator or not. Now, let us find out the adjoint operator, and in one of the classes I have explained how to find out an adjoint operator given an operator. Now, our operator L is del t minus del square del x square. Okay. So, you just okay. So, that means your corresponding equation for del g was del g del t del square g del x square delta x minus x naught delta t minus t naught. Okay. Now, you multiply both sides of this equation by g star. Let us say g star is the adjoint Green's function. Okay. So, okay, you need not to multiply this side. The way you have done the ordinary differential equation, we have considered one ordinary differential equation like including u du dx d square u dx square, and how did you find out the adjoint operator? What you did, you considered the integral. Suppose Lu is equal to 0, that was the operator, that is the equation we are considering. Okay, in probably 3 or 4 classes back. What we did, we considered the integral VLU, and it was turned out to be right Jacobian factor JUV plus VL star U, right, and for the homogeneous boundary conditions, this Jacobian would have been turned out to be 0, and you would have got the corresponding L star. The same thing you can try out in case of a partial differential equation. Okay. That means, in this case, what is your LU? It is basically LG. What is LG? LG is nothing but del g del t minus del square g del x square. Okay. So, you multiply, you consider this integral g star del g del t minus del square g del x square. Now, what you on what you are carrying out this integration? This governing equation is valid for the whole volume. What is the volume in this case? It is a 2-dimensional problem. It is basically dx dt. So, it will be a double integral instead of single integral in the previous case, because in the previous case it was a ordinary differential equation. So, this will be dx dt, one integration over x, other will be over t. Okay. So, consider this integration g star del g del t minus del square g del x square dt dx over on integration over t, another over x. Okay. So, this will be basically g star del g del t dx dt minus g star del square g del x square dx dt. So, this is basically two integrals. Okay. Now, you just do a a partial integration by parts over t first in this part. Okay. So, this is t, this is over x, change the order of integration dt dx. Okay. So, integral over x, first function integration of the second function with respect to t. Okay. First function g star, integration of second function will be g, evaluated what is the limit of t, 0 to t, 0 to t at any point of time. So, it will be from 0 to t minus, right, differential of first function del g star del t, and this will be g dt, this is over t dx, right. So, I am expanding this integral, the inner integral first. Similarly, we will be doing an integration over x first in this case, because you are having del square g del x square here. Since you are having del square g del x square, we are going to have an integration over x by parts first and keeping the other integral outside over t minus t, first function integration of second one what, that is correct. So, 0 to 1 that is okay, minus integral del g star, that is correct, del g star del x del g del x dx dt, that is all right. Okay. Now, this limit, since this integration is done over x, this limit must be over x, x equal to 0 and x equal to 1. At x equal to 1, whenever you will be defining your g star, all the Green's functions are homogeneous. That means, by this you are fixing the boundary conditions on g star. G star has to be homogeneous. So, g star has to be equal to 0 at x equal to 1 and it has to be equal to 0 at x equal to 0. So, there will be no contribution from this part, and in the process you are fixing up the boundary condition on g star. Okay. At x equal to 1. Okay, we will be doing some more one more integration by parts here. First function integration of second function. Okay, that one more step will be there, and we will be fixing up the boundary condition. Now, now evaluate this thing, g star at any time of t, g at any time of t. G at any time of t is not known, but when you put the lower limit, g star right, g at time t equal to 0 equal to 0. So, the lower limit is gone, the upper limit is still hanging in the air. Okay. So, you can just fix like exactly like this, you can fix up the initial condition on g star as well. G is equal to 0 at time t equal to 0. So, you need to bother about the lower limit, and whenever you are writing down the expression of g star, you are giving a Dirac delta function at a different location. Of course, it will be at x1 and t1, right. G star will be xt x1 t1, right, and g was right xt x0 t0. Both functions are different, so you cannot have unity impulse at the same location. Let us say dummy variable at x1 t1 at G star and you have put the unit impulse in case of G at x0 and t0. Okay. Therefore, so these will be a part of Jacobian term in the ordinary differential equation, if you remember. So, this part has to be gone. So, G star at time t equal to 0, time t equal to t must be equal to 0. Then only this term will vanish, because G at any point of time is non-zero, because you know only one condition on G at a particular time point, that is time t equal to 0. At any point of time G is not equal to 0. If G equal to 0 at any point of time, you would have got a trivial solution. Every time it is 0. Okay. So, to vanish, to force this this Jacobian term to go off, the only option you are having, G star at time t equal to t should be equal to 0. Okay. And this t must be greater than t1. Okay, fine. If you just think coolly, then you can follow the logics. Okay, once you fix the boundary conditions on G star, then your whole bilinear concomitant term or Jacobian term will be gone. So, you can go ahead with the integration. So, what is left is integration over x and t G del G star del t dx dt. Okay. Then this term is 0. So, one more integration by parts here. Okay. Taking this as a first term, integration of the second, so it becomes G minus differential of the first, so it becomes del square G del square G star del x square, and integration of the second, so it becomes G. So, you convert all the terms associated with the operator from G to G star. That was the idea. You convert all the terms of dependent variable associated with your operator G, you convert every term to G star. Okay. So, if you convert, if you do that, then what you will be getting is plus minus minus plus t del G star del x times G x equal to 0 to 1 minus del square G star del x square G times dx bracket close times dt. This integration over x. Now, G at 1 is 0, G at 0 is 0, no contribution from this term again. So, this becomes minus x t G del G star del t dx dt minus this integral. So, this term is 0, t x del square G star del x square times G dx dt. Okay. So, what do you get? You get G minus del G star del t minus del square G star del x square dx dt, right. So, it is in the form of VLU is equal to, all the bilinear concomitant Jacobian terms are equal to 0, U L star V. Okay. So, what is L star? L star is minus del del t minus del square del x square. Therefore, you can conclude L is not equal to L star in this particular case. Your L was del del t plus minus del square x del square del x square. Here it is minus del del t minus del square del x square. So, L is not equal to L star. So, it is not a self adjoint operator. So, you have to really find out adjoint Green's function in this case. So, L is not equal to L star. So, you have to find out adjoint Green's function. Okay. Okay. Now, if you remember the property, the relationship between G and G star x naught t naught at x1 t1 should have been G x1 t1 oblique x0 t0. This was the relationship between G and G star that we have derived for one dimensional problem. right, if you remember. So, by this we said you for the way you have found out Green's function, in that rigorous way you need not to find out adjoint Green's function. Using this connective relationship between G and G star, by changing the indices and the by interchanging the independent variables, you can get adjoint Green's function, solution of adjoint Green's function from the Green's function. Okay. So, let us do that. Let us first write down the expression of G, Heaviside T minus T naught summation 2 sin n pi x sin n pi x naught exponential minus lambda n square t minus t naught. Okay. That is the expression of G. Now, you change the variable x t into x1 t1. Okay. You change x and t to x1 and t1. G x1 t1 x0 t0 will be getting this t becomes now t1 minus t0 summation 2 sin n pi x sin n pi x naught, they are product. So, does not matter. So, exponential minus lambda n square t minus t naught, okay, right, x t to x1 t1. So, x should be x1, t should be t1. Okay. Now, G x1 t1 x0 t0 should be equal to G star x0 t0 slash x1 t1. That means, this same expression. So, this will be replaced by G star x0 t0 slash x1 t1 is equal to this, because of this relationship. Okay. Now, let us write down a clear cut expression of G star. So, G star x0 t0 slash x1 t1 should be equal to h t1 minus t0 summation to sin n pi x1 sin n pi x naught exponential minus lambda n square t1 minus t0. Okay. Now, in adjoint Green's function, we are giving unit impulse at x1 t1. Okay. So, the dummy variable x naught and t naught should now be replaced by the running variable x and t. To x and t. So, you will be getting a proper expression of G star Okay. Now, this Heaviside function, it has some implication. Now, the way we have defined Heaviside function, let us say t minus t0 equal to 0 for t less than t naught is equal to 1 for t greater than t naught. Now, whenever you are writing h t1 minus t, this means 0 for t t1 less than t, that is equivalent to t greater than t1. Okay, is equal to 1 for t1 less than t, that means t less than t1. Okay, right, t1 greater than t. Okay, that means t less than t1. So, my adjoint Green's function is defined when t is less than t1 and it is 0 when t is greater than t1. Okay, fine. Now this is a cross check of the boundary condition. Whenever we have the boundary, the Jacobian term that put fix the initial condition on G star, that it is 0 when t is greater than t1. Okay, that is being confirmed and cross checked here. Okay, once you got the governing, okay, fine. So you have got the expression of G star. Now you have to connect G star with U, exactly like G and U, and connect and integrate. Okay. So for that, what you have to do, if you remember, you have to write down the expression, the governing equation for G star. What is the expression for G star? L star G star is equal to delta x minus x naught delta t minus t naught. X minus x1 t minus t1, that is correct, right. What is L star? It is minus del t minus del square x del x square. So it will be minus del G star del t minus del square G star del x square is equal to delta x minus x1 delta t minus t1, right. That is the governing equation for G star. And what is our governing equation for U? U was del u del t minus del square u del x square is equal to f of x t in general, where f is a known prescribed function. Now, how to connect them? You multiplied this equation, let us say this is equation number 1, this is equation number 2. You multiply equation number 1 by u, you multiply equation u dx dt. Okay, multiply equation number 2 by g dx dt, subtract, integrate and subtract. That is how you can connect two differential equations. So if you do that, it will become, I am writing it over volume. Volume means it is basically double integral dx dt. G star del u del t minus G star, I am writing this is as the first one, okay, 2 into G star minus 1 into u, okay, G star del square u, this is over v dv del x square dv plus u del G star del t dv minus minus plus. So again 1 minus minus plus u del square G star del x square dv is equal to over volume, this integral over volume is basically dx dt, f of x t G star dv minus u of x1 t1, okay. That is by the property of Dirac delta function. So you can write, you can evaluate all these integrals and get u as a function of x1 and t1. Let us simplify all this. So it is basically whole lot of left hand side. G star del u del t plus u del G star del t dx. I am just collecting all the various terms and writing it down, minus over t I have collected these two terms, G star del u del t and u del G star del t. So so if you carry out the integration over x, on the outside it becomes d dt of u and G star, okay. Minus first function G star del u del x over x equal to 0 to 1 minus integral del G star del x del u del x dx, okay. This integration is over x from 0 to 1. The second term will be, there will be 4 terms. So these two will be combined here, one is simplified here, another I am going to simplify by parts. First function 0 to 1 minus integral of first function Okay. Now, what is this? These two can be combined like this. Okay. Now, if I integrate over t, what will be the integrand? Result will be u g star evaluated at t equal to 0 and t equal to t1, but still the outer integral remains. Okay. Now, del g star del x del u this will okay, at x equal to 0 and x equal to 1, g star equal to 0, no contribution from this term. At x equal to 1, u is equal to something non-homogeneous, p or something, right? Just look into it, was p, and del g star del x star evaluated, you have an analytical expression of g star, you can take the derivative of g star, evaluate at x equal to 1, so it will be non-zero. So, there will be a term remaining over here, minus at x equal to 0, u is equal to 0, some value was given because it is a non-homogeneous boundary condition, a q or something. So, p at 1 u is equal to 1, it was q, fine. So, q times del g star del x evaluated at x equal to 0. So, you can get that. Now, this will be minus plus double integral del g star del x del u del x dx dt. This will be plus minus del u del x del g star del x dx dt. These two terms will be identical and opposite. So, they will be cancelling out. Okay. So, you will be getting from 0, and what is t? Domain of t from 0 to t1. Okay. From 0 to t1, because above t1 it is all 0. So, it does not matter. So, 0 to t1, it will be u at 1 del g star del x evaluated at x equal to 1 minus u at 0 del g star del x evaluated at x equal to 0 bracket close dt. Okay. Now, what about this? This will be from x equal to 0 to 1 u g star u at t1 u g star at t equal to t1 minus u g star at time t equal to 0 dx plus these two terms, these two integrals. So, let us say t1 minus t2, this whole thing is t1 and this thing is t2. Okay. At t is equal to t1, your g star is gone, g star equal to 0, there is no contribution from this. Agreed? At time t equal to 0, g star is still present. It is not equal to, because on the time it is defined on t1. Okay. At right. So, in the limit at t equal to t1, you can consider it to be 0, because when t is less than t1, it is definitely 0. T greater than t1 is definitely 0. T less than t1, it is non-zero. At t is equal to t1, let us say it is 0 in the limit. Okay. At time t equal to 0, g star must be existing, it is non-zero there, and that can be evaluated from your, you have an expression of g star, so just put t equal to 0, you will be getting that expression. It is exponential term will become 1. Okay. And at what is u at time t equal to 0? It is non-homogeneous, it is h, whatever, p or h, whatever. So, that will be coming here. So, you will be getting 3 integrals, and finally, on the in the left hand side you will be getting, that is h, I think, minus 0 to 1 h of x g star evaluated at t equal to 0 dx plus 0 to t1 q del g star del x at x equal to 1 dt minus 0 to t1 p del g star del x at x equal to 0 dt. That is the left hand sides. Now, on the left hand side you will be getting 3 non-zero integrals. These 3 non-zero integrals, if you just check, they will be corresponding to 3 non-zero homogeneous condition, one on the initial condition, the other two on the boundaries. So, there will be on the initial condition, since the initial condition is not homogeneous, this integral is over x. On the boundaries, boundary conditions are not homogeneous, that is why these integrals are over t. Okay, then you just collect all the terms, u x1 t1 will be 0 to 1, 0 to t1 f of g star dx dt plus h g star at 1 at t equal to 0 dx 0 to 1 minus 0 to t1 q del g star del x at x equal to 1 dt plus 0 to t1 p del g star del x at x equal to 0 dt. Okay. So, and f, h, q are known. Let us say all these are constant, or f will be a known function of x and t. Okay. Let us say x, it may be 2x, it may be 2x square plus 3t, something like that. H, p, q all are known functions or constants, and expression of g star are known to you. Okay. Now, g star will be having two variables, one is running variable x and t, other will be a dummy variable x1 and t1. You are integrating over the running variable x and t. So, finally, whole lot of right hand side will be function of x1 and t1, some functional form that you can evaluate all these integrals analytically, okay, exactly like the previous problem. So, you will be getting x1 t1 is equal to, let us say, k of x1 t1, lots of summation terms, 1, 2, 3, 4 terms. One, this term corresponds to the non-homogeneity in the governing equation. Since it is applicable through the whole volume, you are getting a double integral. All the threes are on the boundaries. Time is also boundary, since it is time, it is called initial condition. Okay. Now, once you get u as a function of x1 t1, change them into running variable x and t, you will be getting the solution of u as a function of x and t. Okay. So, that is how you will be getting the solution of non-homogeneous parabolic partial differential equation with the non-homogeneous boundary conditions as well. Okay. So, the syllabus will be up to this, and let us see how it goes in the exam. Yes. Okay. Thank you very much.